Okay, so the packet I just gave you, we're going to be starting on that. Our goal with this is to understand the relationship between vertical asymptotes and infinite limits. What we'd like to be able to do is we would like to be able to, given a rational function, such as f of x equals, say, x plus 1 over x squared minus 4. We want to be able to graph something like that without using the graphing calculator, just by using some calculus methods. So that's our goal. Another thing we want to be able to do is to understand the behavior of graphs. For example, if I have a graph that looks like this, let's say I have a vertical asymptote here. I might have the function going way down like this and then way up like this. Based on this, I would know that the limit as x approaches 1 from the negative side, see what's happening as we approach an x value of 1, what's happening to our y value is going way down here. So we can call that negative infinity. So that limit right there would be negative infinity. If I changed it and said the limit as x approaches 1 from the right, here's 1 from the right, see what's happening? Now it would be positive infinity. Now, that's what we're going to be looking at. We want to be able to find those kind of limits without just looking at the picture, by doing it in a more algebraic method. So first of all, when does a function have a vertical asymptote? When does that happen? Madison? When the denominator equals... So this is going to happen when denominator equals 0 and does not cancel with numerator. So what type of continuity do we have at a vertical asymptote? Joe? Removable or non-removable? Yep, we have a non-removable discontinuity. And this is very important. So if a function approaches a vertical asymptote, the limit does not exist right there. However, the behavior of the limit can be described by using values of infinity or negative infinity. So even though we don't have a limit here at x equals 1, we do have a description for what the limit is as x approaches 1 from the left and as x approaches 1 from the right. And we need to understand how this works numerically. So when I have some constant, let's say I have a constant of 1, and I divide that by a number very, very small, like 0.0001. Look at my answer, 10,000. So what if I make that number even smaller and I divide by 0.00001? Now look at it, 100,000. Let me add on another decimal place. So can you see what's happening there? As I divide by something that's smaller and smaller and smaller, what's happening to the result? It's getting much larger. And so this is actually, what, 10 million it looks like? So what are we approaching then? Infinity, right? So that's the reason why if I have a constant divided by a very small number, it's going to be infinity. And if I have a constant divided by a negative that's very, very close to 0, it's going to be approaching negative infinity. Well, this is important. This is something that we're going to be using throughout this section. So it says, if f of x equals 1 over x minus 1, find the following. What is the vertical asymptote? Peter, what's the vertical asymptote going to be? What makes the denominator equal 0? 1. So the vertical asymptote is going to be at x equals 1. So now we want to find what's the limit as x approaches 1 from the left. And we haven't done this before, but what we're going to do is we're going to plug in a number that's really close to 1. See, I can't plug in 1, I'm getting it 1 over 0. So I have to plug in something really close to 1, a little bit smaller though. So in for my x, I'm going to plug in 0.999. So I'm plugging in something as close as I can to 1 from the negative side. And the only reason I'm doing that is because I can't plug in 1. If I could plug in 1, I would. So when I do this, I'm going to get 1 over 0.999 minus 1 is negative 0.001. So looking up above, what's that going to be equal to? Negative infinity, right? That's what we just did up here, guys. It was approaching negative infinity. Now I'm going to plug in a value for 1. I can't plug in 1 exactly, but I can plug in something a little bit bigger, such as just slightly bigger, 1.001 minus 1. Plugging that in right here. So when I do that, I'm going to have 1 over, subtracting that, I get 0.001. And then looking up above, that's going to be infinity. So now I've just kind of proved the way that function is going to look. We already looked at this one earlier, but look, you've got 1 divided by x minus 1. Here's what's happening. As I approach 1 from the negative side, we're going down to negative infinity. As we approach 1 from the positive side, we're going up to positive infinity. Okay, so let's look at example 2 now. Find the limits as x approaches the vertical asymptotes from the left and as x approaches the vertical asymptote from the right. So first we have to identify the vertical asymptote. Casey, what is it? Where's the vertical asymptote? 3. It's going to be at x equals 3. So now I have to find the limit as x approaches 3 from the left. So I'm going to plug in something slightly smaller than 3. So I'm going to plug in like 2.99. I'm just plugging that into my original function. So when I do that, I'm going to have 2.99 minus 3. That's negative 0.01. But if I square it, that's going to be positive 0.001. And what's that equal to if I have a constant divided by 0.001? That's the same thing as infinity, right? So this is going to be infinity. Now we have to do the limit as x approaches 3 from the right. So think about what number I would plug in if I want to just be slightly to the right of 3. I'd love to be able to plug in 3, but I'm going to get 1 over 0, which is undefined. So I have to plug in something to the right of it. Matthew, can you think of something just slightly bigger than 3? Yeah. Okay, that's pretty close. Let's go 3.01 just to make it even a little closer. So we're going to do 1 over 3.01 minus 3, and we're going to square it. So when we do that, we get 3.01 minus 3 is 0.01. We have to square that, and we get 0.001. And so what's that equal to then? Nick, what's that going to be? 1 over 0.001. Yeah, but as far as our purposes, we know it has to be infinity, a negative infinity. Yep, it's going to be infinity, isn't it? So what that's telling us then is that for this function, if I have that typed in, and I look at the graph of it, as we approach 3 from both sides, see how it's going up to infinity? As I get closer to 3 from the left, it's going up to infinity. As we get closer to 3 from the right, it's going up to infinity. And that's what we had, infinity and infinity. See how that's helpful? Okay, example 3. Use the function below to describe when a function has a hole in the graph and when the function has a vertical asymptote. What has to be true for us to have a hole in the graph? The factors have to be what? The same, right? So I would have to say to get a hole in the graph that f of x could equal g of x, right? And those both would have to equal 0. that would cause us to have a hole in the graph if that happened. Well, to get a vertical asymptote then, I could look at h of x. Could h of x equal f of x? No, it has to be different, doesn't it? So to get a vertical asymptote, h of x could not equal f of x, but h of x would have to be equal to 0. So see, if those functions, f of x and g of x, are the same and they equal 0, that's going to result in a hole in the graph. If h of x is not the same as f of x, but h of x does equal 0, that's going to result in a vertical asymptote. That's just kind of like an abstract way of saying everything that we've done. Example 4. Use the function below to find vertical asymptotes and holes in the graph. Avery, what do we have to do first? Yep, so we're going to factor the numerator, that's x plus 4 times x minus 2. Factor the denominator, that's x plus 2, x minus 2. Kyle, do you notice anything about that? Do we have anything that's equal? Right, so because these two cancel, what's that going to mean then, Kyle? We have a what? Right, and I'm going to be even more specific. We have a hole that, he's right, x equals 2, but I'm going to plug it back in to find the specific point. So 2 plus 4 is 6, 2 plus 2 is 4, 6 over 4. Here's exactly where the hole in the graph would be, at 2 3/2. Now the other factor in the denominator did not cancel out. So now what's that going to mean? Right. At x equals what? Right. See how that would help us to graph if we knew that information? That's where we're going with this. On our next quiz, you have to be able to graph these rational functions without a graphing calculator. And this would help you to do that. All right. So on these, find all vertical asymptotes, which are non-removable discontinuities, and holes, which are removable discontinuities, for each of the graphs. I want you to think about number 1. Get your answer ready. Mindell, what do you think? Okay, so non-removable, which is also known as a vertical asymptote, at x equals -1. Do we agree? Yes or no? Yep, that's right, isn't it? Right, what about number 2 then? Michael, what should we do first on number 2? Good. Would the numerator factor? Okay, so what does that mean has to happen then? Good. Tell me them. Good job. So we can have 2 vertical asymptotes. In fact, if we look at this one, see, you can use your calculator to help support what you think is true. And we think that there should be 2 vertical asymptotes. Let's look at them and see. Here's the way the function looks. We've got the vertical asymptote at 1 and -1. See how if we knew the limit as we approach those vertical asymptotes, it would be helpful for us to be able to graph the whole thing? That's what we're going to do eventually. Okay, number 3. Cotangent of x. Does it have any holes in the graph for cotangent? No. It's got vertical asymptotes though. People always forget where those vertical asymptotes occur. Does anybody remember? Well, if not, we need to think of 0, pi over 2, pi, 3 pi over 2, and 2 pi. We need to think of that unit circle and those quadrantal points. So this point right here, that point right there is going to be 1, 0. This point here is 0, 1. This is negative 1, 0. This is 0, negative 1. What's the ratio for cotangent? Jackson, do you remember? Is it like y over r, y over x, x over y? It is x over y. So if I want to know where I have vertical asymptotes, I want to know where what equals 0, x or y, guys? Y, yes. I want to know where is y 0. So I can look at this. Is y 0 here? Yes. Here? Here? Okay. So some places where I'd have vertical asymptotes then. What about even if I go in this direction? What do I call it if I go in that direction? What do I call that angle? What is it, Natalie? Negative pi? Yeah. So I would have vertical asymptotes at negative pi, 0, pi, 2 pi. How could I write that a little bit better instead of making people figure out what they are? X equals what? There you go, k pi. K can be any integer, so 0 times pi, 1 times pi, negative 1 times pi. All of those would be where the vertical asymptotes occur. Okay? Any questions? All right, guys, you have your assignment on your assignment sheet. Make sure you have that ready.